Alright, before we start the video, I recommend you to watch this first. If you're done, let's get into it. Recall that in rigid body mechanics, we can define position factor here as R capital factor plus rho factor, which equals to R factor or position factor, which R capital here is central mass from origin, and then rho factor here relate to distance between central mass and its point, which in this case, the rate of change of rho factor length here is equals to 0. This tells us that distance between elements is constant implicitly. And now the question is, how if rho length rate of change is non-zero? In the first early video, we built the system of our physical system from particle and then rigid body just like before, and then we will level up to something beyond all of them. To answer the questions, first we assume that our system here has continuous distribution or at least integrable distribution. For example, we have fluid flow, which all body of fluid has different velocity factor and direction, and then electricity and magnetism, and then temperature difference between time and space, and etc. So that means our system here needs a partial differentiation, which equation of our dynamic here will lead us to partial differential equations. And by the assumption, we can build our system as a collection of coupled springs just like this, which make our system has continuous distribution or at least integrable distribution. In our system, let's say this particle here as our origin point in our coordinate system. So that means all position factor begin from this O to other particle just like R1, R2, and so on for all position factor of all collection of particles. So then, if we take the force applied on J element of our particle and we project to some axis, let's say I, then it will equals to this in M multiplied by A factor, and the equality again for spring system as this. Here, J index is about level of particle in our system. And by this, we can just simplify to this. So then, if we take all sum by J and take the smallest region, let's say V capital or volume, which is this V capital's approach to 0, then the summation will be like this. If we multiply the both sides by V capital, then by assumption that spring doesn't break, this equality can be integration rho along volume element, and the other side here is integration by mu, which is mu is about this equality that proportional to force over area value. And by using the composition as rigid body, which now we have displacement from initial position, then we can switch these equations to only explain about displacement, which now the equation will become as this. In this equation, we have found that C here is what we know as field, which this may be a scalar as f of x, or a vector as a vector of x, or a tensor like I double arrow, and etc. And notice that in this partial differential equation, nabla C here is about gradient, but what about nabla dot nabla C? I will keep this for next video. And notice that the all here is an introduction to other region of physics as field theory. And that's for video today about introduction to field theory. I hope you enjoy this video. If you like this video, don't forget to share and subscribe. If you have any question, just drop a comment below. And thank you. See you next time.